Hello students, welcome to Nirachal Polytechnic. We are continuing with the calculation of force exerted by jet of water on the curved plate. As shown in the figure, we are having a curved plate. It is having 2 points, inlet tip B point, outlet tip E point. To find out the force exerted by jet of water, we have to take the need of the velocity triangles. The velocity triangles will be drawn according to the information related to the velocity of jet, relative velocity and the blade velocity. This is the triangle which shows that how the velocity of jet, velocity of blade and relative velocity and velocity components are there in the inlet and outlet. How to draw these triangles, velocity triangles at the exit and inlet of the curve plate. After assuming that there is a curve plate, the jet of water is striking at the inlet tip B point. We know that the jet symbol is pipe with a nozzle. Velocity is a vector quantity, so it is represented by a line with a arrowhead. A point is the exit of the nozzle, B point is the tip. The force is exerted by the jet of water from A point to the inlet tip. So A to B is the vector and that is your velocity of jet. The velocity V1 is making an angle of alpha 1 at the horizontal line. So it is having two components. One is your horizontal component, another is your vertical component. V1 sin alpha, it is Vf1. V1 cos alpha, it is Vw1. So Vf1 is a flow velocity of water at inlet, Vw1 swirling velocity of water at inlet, and V1 is the velocity of jet at inlet. We know that the jet is moving with a velocity v, the blade is moving with velocity u. There is a resultant velocity with which the liquid enters to the curve plate. We have seen that from B point, where a extension from B point to that of the horizontal line where it is intersecting, that point give us C point. This is the relative velocity of jet of water which is moving tangentially through the internal surface of the plate. So how to find out that velocity of water? So we have to extend the internal curved surface line from B point. We have to take a line, extended line, and that will crossing the horizontal line at the point C, and this is denoted as Vr1, that is relative velocity at 1. From A to C, that is known as your velocity of blade, and Vr1 is the relative velocity, V1 is the velocity of jet. So we have obtained that there is a triangle made by jet velocity, blade velocity, and the resultant component is your relative velocity. So we are getting A, B, C is the inlet velocity triangle, and the V1 component having horizontal component as Vw1. So A to D is your Vw1. Vertical component is B to D, and that is your Vf1. In this way, we are going to draw that ABCD triangle, which gives us the result that alpha is the blade angle made by the jet velocity with the blade velocity of blade. Relative velocity of jet of water makes an angle of theta, or that is theta 1 at inlet. So we have to find out that what is the initial velocity of the water. We know that force, calculation of force, we have to calculate mass of water flowing per second into initial velocity minus final velocity. So initial velocity means what? That is your VW1 minus U. Let's comes to the outlet velocity triangle. The velocity of water, that relative velocity of water enters causes the flow of water which is moving tangentially throughout the internal surface of blade. Now we have to extend the line from point E, and that line is suggesting the VR2, that is relative velocity of water from point E. That is makes an angle of theta 2 at outlet, and that is known as your relative velocity at outlet. And that is vane angle at outlet is theta 2, and that is angle made by the field. Similarly, the jet velocity at inlet is V1, but after the striking the jet at the inlet tip, it is also exited. So where the blade is continuously rotating, so it is obtain the force at inlet and exit the velocity of jet at a velocity V2, and E to F, this is the velocity of jet of water which is crossing the horizontal line, and that angle is alpha 2. That is blade angle at outlet. This V2 velocity having two components, and vertical component is Vf2, horizontal component is Vw. Flow velocity of water at outlet is Vf2, whirling velocity is at Vw2. The triangle EFG is known as your velocity triangle at outlet, where we are getting the relationship that velocity of jet, velocity of blade, and the resultant velocity VR2 at the outlet. We are having the AEFGH triangle, where we are getting the different relationship between the velocity of blade, velocity of the jet with its velocity components along x direction and y direction. Now we are going to calculate the value of force exerted by the water upon the blade. As shown in the figure, we are having velocity of u at outlet, and velocity of component hurling is Vw2. The final velocity will be obtained as minus u minus Vw2, because it is in reverse direction the flow of liquid takes place. So the force exerted by jet of water can be obtained as Fx is equal to mass of water striking per second into initial velocity minus final velocity. The initial velocity is Vw1 minus u1 minus final velocity is minus of Vw2 minus u2. We are getting that if the blade diameter is constant from inlet to the outlet, then we are getting u1 is equal to u2, and lastly we get Vw1 plus Vw2. We know that the velocity with which the water striking the curved blade is relative velocity, that is Vr1. Hence the mass of water will be equal to rho a V, where V is known as your relative velocity Vr1. So finally we are getting that Fx value is rho Vr1 Vw1 plus Vw2. The general expression can be written as Fx is equal to rho a Vr1 Vw1 plus or minus Vw2. That depends upon the outlet velocity of jet, what is making an angle of beta. So if the jet velocity of water at outlet is more than 90 degree, then we have to use that Fx is equal to rho a Vr1 Vw1 minus Vw2. But if the value of beta is below 90 degree, then we have to use Fx is equal to rho a Vr1 Vw1 plus Vw2. Now let's consider if beta is equal to 90 degree, then the velocity triangle will be reduced to vertical component V2 is equal to Vf2 and Vw2 equal to 0, and Fx is equal to Vw2 value 0, so Fx is equal to rho a Vr1 Vw1. Next, if the angle beta is at an angle of beta more than 90 degree, then what we are going to see, there will be negative sign occurs and Fx is equal to rho a Vr1 Vw1 minus Vw2. If you are going to find out watt done per second, then what we have to do, watt done per second Fx is equal to Fx into U. If you are getting the efficiency, then watt done per second of water divided by kinetic energy of water per second. So that is equal to rho a Vr1 Vw1 plus or minus Vw2 into U divided by 1 by 2 rho a Vr1 into V square. So rho a Vr1 will be cancelled out and rest of term will be equal to 2 Vw1 plus or minus Vw2 into U divided by V square. So we are concluding that the value of Fx, that is Vw1 plus or minus Vw2, depends upon the angle of jet of velocity at outlet, beta value. If 90 degree below beta value, then we have to write plus. If it is above 90 degree, then we have to write minus. Thank you.